Welcome to this explainer. Today, we're looking at what is probably the most extreme double-edged sword of our technological future. We are standing right on the precipice of a new era in computing, one that promises to totally unravel the digital fabric of our society, while simultaneously offering us the exact tools we need to pull humanity back from the brink of climate catastrophe.
Okay, let's dive into this because it's honestly an incredible, almost cinematic paradox. Think about it. We're racing to build quantum computers that literally have the power to utterly wipe out all modern digital privacy. Yet, those exact same machines, they might be the only tools capable of modeling the molecular breakthroughs we desperately need to halt global warming. The tension here is just immense. So figuring out how these two massive realities collide is absolutely crucial for us to understand.
Section 1. The approaching Q-Day threat. To really grasp the stakes here, we first have to look at the terrifying, immediate threat that quantum computing poses to our global cybersecurity. Experts actually have a name for this looming milestone, Q-Day, or sometimes you'll hear it called Y2Q. Basically, this is the hypothetical day a quantum computer finally becomes powerful enough to just shatter public key cryptography. And look, this isn't just some vague, distant thought experiment. Thanks to a mathematical breakthrough way back in 1994 called Shor's algorithm, we know for a fact that a big enough quantum computer can efficiently factor the massive numbers that secure all our data. The math is completely proven. It's a mathematical certainty. We're essentially just sitting around waiting for the hardware engineering to catch up. So the crucial point here is, well, not all encryption is doomed, but the parts that are doomed, they're completely foundational. Symmetric encryption, like AES, where both sides share a single key, actually survives. You basically just need to double the key length to stay safe. Easy enough, right? But public key cryptography, things like RSA and elliptic curve cryptography, completely 100% broken by Shor's algorithm. And that's a massive problem because public key encryption is the literal handshake that secures HTTPS web browsing, your virtual private networks, software updates, and the entire global banking system.
So how close are we on the hardware front? Well, just a few years ago, experts thought we'd need around 20 million noisy physical qubits to crack an RSA 2048 key. But recent 2025 research from Google Quantum AI figured out how to run the algorithms way more efficiently, bringing the requirement down to well under 1 million physical qubits. Now, the largest deployed processors in 2026 only have around 1,180 noisy qubits. So sure, the gap is still large, but the target is shrinking incredibly fast. And that aggressive downward trend is exactly why security experts are on high alert right now.
Section 2. Harvest now, decrypt later.
And that brings us to why this is an absolutely urgent problem right this second, even if the hardware is still years away. The absolute most chilling part of the quantum threat is a surveillance strategy known as harvest now, decrypt later. You see, adversaries don't need a working quantum computer today to read your secrets tomorrow. They're just recording encrypted traffic right now, hoarding it in massive data centers and waiting. There's this concept called Moska's inequality. It basically states that if the time it takes to secure our systems, plus the time our secrets must remain confidential, is greater than the time until a quantum computer arrives, well, we're already exposed. Because of this hoarding strategy, any data that needs to stay secret for decades is essentially already compromised. We're talking about things like diplomatic cables, your personal health records, critical infrastructure logs, highly sensitive intellectual property, and defense secrets. If this data was sent over an exposed channel using current public key cryptography, the deadline to protect it wasn't Q-Day. It was literally the day you sent it.
Section 3. The quantum reality is here.
Now, you might be thinking, okay, this all still sounds a bit like science fiction, but we really need to pivot from the theoretical threat to the tangible, present-day breakthroughs proving this tech is advancing at breakneck speed. Check this out. On March 26, 2026, IBM announced a massive milestone. Using a quantum-centric supercomputing workflow, they accurately simulated the quantum properties of a real magnetic crystal, specifically KCUF3. But here is the kicker. Their quantum simulation perfectly reproduced actual neutron scattering data gathered from the spallation neutron source at Oak Ridge National Laboratory. They proved definitively that current quantum processors can capture the dynamic properties of real materials that classical computers simply cannot model accurately. And this brilliantly illustrates a massive turning point. As Arnab Banerjee from Purdue University pointed out, comparing these quantum simulations with experimental data has been a decade-long dream, and now it's finally a reality. The scientific community sees this as a huge raising of the bar. Quantum computers are no longer just quirky laboratory curiosities, They are becoming reliable, totally essential instruments for real-world scientific discovery.
Section 4, solving the climate crisis. And this exact capability, the sheer power to perfectly simulate molecular chemistry, completely flips the narrative entirely. It reveals the massive, awe-inspiring upside of our quantum future. According to research from McKinsey, applying quantum computing to our most stubborn sustainability challenges could facilitate a staggering 7 gigatons of annual CO2 reduction by 2035. To put that into perspective, applying quantum computing to climate tech could actually be the decisive factor that puts the critical 1.5 degrees Celsius global warming target back within our reach. That is massive.
Now, what's really interesting about this is exactly how that 7 gigatons gets achieved across completely different industries. By perfectly modeling molecular chemistry, quantum computers can help us understand electrolyte complex formation to create EV batteries with 50% higher energy density. That alone saves 1.4 gigatons. They can also model the exact energy state of pulse electrolysis and catalyst interactions to make green hydrogen production 100% efficient, saving another 1.1 gigatons. And they can rapidly simulate theoretical material combinations to discover zero-emission alternative clinkers for cement, shaving off a full gigaton of emissions. It's like having a cheat code for material science.
And it goes even further into active carbon removal. Direct air capture is currently incredibly expensive, but quantum models can help us design novel adsorbents, like metal organic frameworks or moths. Essentially, these materials act like giant carbon sponges, but predicting their exact molecular properties is just way too complex for our standard classical computers. Quantum simulation, on the other hand, can optimize them, potentially dropping the cost of carbon removal to the critical $100 per ton threshold. That would make massive-scale direct air capture actually economically viable. And just look at the sheer diversity of these green breakthroughs. On one side, we have energy generation, where quantum computers can simulate perovskite crystal structures to push solar cell efficiency up to an incredible 40%. On the entirely different side, agriculture. Right now, cattle produce huge amounts of methane. With precise molecular simulation, quantum computers can help design methanogen-targeting antibodies for cattle vaccines. Yes, we are actually talking about anti-burp vaccines for cows. That could potentially eliminate up to 1 gigaton of CO2 equivalent without disrupting global food supplies. The reach of this technology across totally different sectors is just staggering.
Section 5, securing our quantum future.
But to reap all of these incredible climate benefits, we absolutely have to survive the cybersecurity threat first. We have to secure the internet before Q-Day arrives. Let's trace this timeline and see how this actually builds a roadmap for our survival. The defense against Q-Day already exists, and it's really all about math and engineering. In August 2024, the U.S. standards body, NIST, finalized the very first post-quantum cryptography standards. Now, in 2026, we're in the era of hybrid implementations, running old and new encryption side by side. And governments worldwide are pushing hard for full migration completion somewhere between 2030 and 2035. So how do we actually do it? Well, the fix requires a multi-layered approach. Organizations must transition to post-quantum cryptography, adopting the new FIPS algorithms, which, by the way, rely on complex structural math called lattices rather than old-school prime factorization. Software systems need crypto agility, basically the engineering capability to easily swap out encryption algorithms as threats evolve over time. And on a hardware level, telecom operators are deploying optical layer encryption, like the systems developed by CyberRidge. This actually buries fiber optic signals in physical noise, so attackers can't even harvest the data in the first place. The big takeaway here? We don't need our own quantum computers to defend ourselves. We just need to rigorously apply this new math and physics.
So this really is the ultimate race of our time. On one track, we have a relentless drive to secure decades of human data against a catastrophic cryptographic collapse. And on the other, the pursuit of molecular mastery that could literally cool a boiling planet. Will we manage to lock down our digital infrastructure fast enough so that when the true quantum era finally dawns, we can actually use these incredible machines to save the world rather than watch them tear it apart? It's a fascinating question, and the clock is definitely ticking. Thanks for joining me for this explainer, and I'll catch you on the next one.